Expecting what? Energy? Well, let's learn. Here on today's question, we are going to take a different approach to a common question, and this approach will be used a lot in the upcoming sections, so let's pay attention. In this question, we're concerned with a particle in an infinite square well has the initial wave function capital Psi x of 0 is equal to big AX for x between 0 and a/2, so the first half of the well, and A, capital A, times little a minus x for x between a/2 and a, so the second half of the well. Part A wants us to sketch this initial wave function and determine a constant A. B, find capital Psi x of t. Remember here, not only do we have a separable solution type set up here, but we're also going to have to determine the unknown coefficients. Just a warning and a heads up. C, what is the probability that the measurement of the energy would yield the value E sub 1? Here indicating that this is N1. And then D, find the expectation value of the energy using equation 2.21. Equation 2.21 takes into account these unknown coefficients, and it uses those as compared to the operator definition of the Hamiltonian, which requires a double derivative. The reason why is because for this type of problem, the function is ill-defined for two derivatives. As you see, we have linear terms in both. So this method has an advantage insofar as the initial wave function is normalizable. So let's check that out. Now, to normalize this, it needs to be handled with a certain level of care due to being a piecewise function. Let's take a note of the boundaries here. Okay, if you wish to distribute this out like a mixed state, you'll end up multiplying by 0 because parts of the function aren't defined over the entire domain. So just remember what our function is telling us per each part. So here we have our normalization condition, of course, what we've been used to, and we have to split it up between 0 and a/2 and a/2 to a. Of course, both of those functions have different definitions there, so we have x squared on one and a minus x, and then we have to square that due to psi star psi, and we have the big A out front of both, and they're both squared. Okay, cool there. And now we're just going to math it out. Pretty easy to deal with here. We see both of these go from a square to a cubic, so we have to divide by a factor of 3. Both of them have it, factor it out. What I'd like to take a quick note to point out is that the 0 here in this lower boundary cancels this term to 0, and the a here in this upper boundary, a minus a, cancels that to 0. So we're just left with the a/2 and a/2 boundaries, which is what we see here. Just do note that we have a double negative here since a here is in the lower boundary, a/2 is in the lower boundary. Once we do that, we see that we have 2 copies of this thing, so we factor that out with the 2 here. And now we see that the 2 over the 8, which was found from cubing at 2 here, gets reduced down to a 4, and then 3 times 4 gives us a 12. So that's how our denominator ended up as a 12, starting from a 3. And then here we just got to solve for big A. So, multiply 12 over, divide by a cubed to the 1 over here. And then we just take the square root, simplify it down. You could keep it as just this, and we'll see, how that might be an advantage later. Doesn't really matter. Whatever makes you or your professor happy, use that. Okay, so really quickly, let's take a look at the graphical result. Here we just have psi x of x and 0, and we see here that it's a kind of tent, but it's a triangle because we have a positive x here, and then we have a minus x here. Again, note that the boundaries happen from 0 to a/2 and a/2 to a, so we get a nice boom boom. Okay, now note that the peak here occurs at a/2. And if we plug a/2 in for the first part of the piecewise definition, that gives us a value of little a divided by 2. Since we're multiplying that by big A, this is our total height here. And if we plug in capital A from what we just found, we'll see it kind of simplifies down. I do have a Desmos version of this as well if you're interested. And all I did there was modify the parameter A, so the width of the well. And with that, I'll see you on the next part. Long time no see. And here we go with the cumbersome math. To find the coefficients, which let's recall that we're doing this because separable solutions, we know we can set up as an infinite set of functions in a linear combination. So we have to determine what those Cn's are going to be for every state n. So to find these, much like we had done in E and M, we are going to exploit the orthogonality of the basis functions for a particular potential. And in this case, what we were told was this was the infinite square well, so we know what the potential looks like. And the orthogonality condition that is exploited here is known as Fourier's trick, and it's used throughout physics because of how beautifully it exploits this orthonormality condition of the set of functions psi n. So we just have to be careful here because as we note here in the first line, the Cn, after we apply Fourier's trick and get the Cn to one side, we're still left with an integral over the entire well. So much like in part 1, we're going to have to split this integral up for the fact that we know that capital psi x of 0 is defined in two parts because it's piecewise. So use the same approach that we did for the first question and split the integrals. Alright. Once we do the splitting of the integrals and we have everything in its set, we see that we factored an a out from the psi here, and we just have the square root of 2 over a, which was a result of the infinite square well solution set, along with the sign n pi over a. So all that came from the solution set for the infinite square well, and this is what we were given. So again, go look at the notes if you want more on that. After we split it here, use a calculator or table to set up and evaluate because these are, you could use integration by parts even. It just becomes very cumbersome. Again, let's focus on the physics here. After that, we just have to be careful of evaluating the bounds of the integrands once we find the antiderivative, and we do that here. I color coded, of course, so we know what blue segment goes with the blue bounds, and the red you have to split up twice. Annoying, I know. But let's pay attention to the cancellations here. Okay, so here you see we have a purple cancellation, a purple cancellation. Those cancel in just a one-to-one fashion. The ones here with the black line, they cancel due to a summation of fractions for their coefficients. Notice that we have a 2 right here, a 2 right here, so the minus sign add them together gives us a -1. And then here we have a matching coefficient, so that's what cancels there. Just be careful in these details because you really don't want to keep, spending a lot of time working with these things and carrying them all down if they cancel due to coefficients. So let math and algebra save you a couple headaches and do it as quickly as possible. What we see here is that we end up with this nice, after the fact, this nice kind of simplification down. You see we have 3 or 4 copies of little a in a square root that gets put down here, and we just combine the 2 inside the square root with the 3 inside the square root to get 6. Again, algebra way. Notice here how we have 2 copies, so let's go ahead and get that tidied up on the next one. So as previously stated, we do have 2 copies, so we're just going to be able to factor out the coefficients to the left and the function to the right, and we just have 1 plus 1. Again, just keeping a color code so we're all together. Here you see that a to the 4th and the square root cancel down to a squared, so we can cancel that a squared with the coefficient a squared. Easy enough. We're left with n squared pi squared, which we see here. The 2 here gets multiplied by the 2 from the bracket, so that's how we end up with this new coefficient on a sine function. And here we know that sine and cosine alternate between plus or minus 1. They're bounded. So now the function takes on whatever amplitude is on that sine or cosine function. What we wish to do is try to create a closed form solution in terms of the allowable states in, and that is what we see here with the -1 nonsense, because we know that we get plus or minus 1 out of sine. and that's all it can amplify this amount by in these even states. So here, or rather in the states allowed, which are n equal elements of the odds. So, we have to be careful here about which ones we can select from the integers. So if we're 0, then we end up with n equals 1. If we're 2, then we end up with 3, and so on and so forth. And so just be aware that this only holds here based on where sign allows for solution, since it's n times pi over 2, which are at odd numbers. So be aware that the notation here is just trying to showcase that we want odd numbers instead of writing out every odd number. So with that, now we can combine all these into one big equation. Let's note that to find the full solution function here, capital Psi x of t, we need the time component, or the temporal component of the separable solution, which is what we have here in the exponential. And we need everything that goes into the psi x, or the spatial partition, which is a collection via linear position, or linear combination of all the basis functions, which is sine x times everything in the coefficient space. So we did all of that because we know that this closed form solution can be summed over everything, and we can calculate explicitly for the allowable states. And in this case, those are states 1, 3, 5, all the odd numbers. So here's the closed form solution for this style of question. And again, we will see these again because most of the solution sets for the next type of potentials are going to be power series solutions to the differential equation. But do note here that En is a general term, and since we were told that this is an infinite square well, we know that this is the En that are allowed, the energy levels allowed, and we will use this in the next step to calculate the probabilities and the expectation value of the energy operator. And coming into the home stretch, we have the probability and the expectation value. Who would have thought this would happen in a quantum mechanics course? However, here, the coefficients represent the probability. Why? Well, loosely speaking, C sub n tells you the amount of lowercase psi n that is contained in capital Psi. Okay, again, very loosely. We have to be careful in quantum mechanics with our language. And so in being careful to note that the language matters a lot in this theory and in this context, we need to know that it's actually the magnitude squared of the coefficients that is the probability. And we say it's the probability of getting the particular energy value of E sub n. Okay, so that's what we see here. Here we were given that we wanted E sub 1, so we have to look for the probability of the state 1, which is the coefficient 1. So if we plug it into the closed form or the form we found on the last couple slides for C sub n, we see we get this nice little magnitude bracket going on. Here I would like to point out that in this particular case of n equal 1, the negative 1 here will settle down to negative 1 to the 0 power, which is 1, which is highlighted here. But in general, all that this negative 1 does is alternate the sign. It doesn't add anything to the magnitude. And since we want the magnitude squared, we normally just leave off the negatives because all it does is cloud up the computation. So once we're done with that and we square everything, you see we get a 4 squared times 6 over pi to the 4th. And this gives us a value that is really high, and we have 0.9855. So that is a very higher probability that the given initial wave function is close to the initial state basis function, which if we compare the graphs of the sine function with this triangle function, yeah, there's very, very close similarities there. So this probability makes a ton of sense. Okay, now for part D, the expectation value of the energy here, well, we have to be a little careful. The angle brackets H, what we need to do is, again, we already mentioned how the operator wouldn't work here because of the derivatives. So we have to multiply the probability of the in-state energy by the in-state energy. So here we set up a probability system where we have the probability here applied to the energy. And we saw that question, we saw this setup with the mixed state question, so it shouldn't look anything totally new. The only thing that we have to worry about here is the kind of maneuvering that we will need in the series expansions. So let's go ahead and simplify this through. You see we get a couple cancellations here once we square this bracket. Again, the -1 doesn't really do anything to the magnitude, so we just leave it off. And you see that the 4 squared goes to 16, and then 6, and then we have into the 4th, pi to the 4th, like we do here. However, what we see here is that the energy states that are allowable for the infinite square root are n pi h bar all squared over 2ma squared. So we get n squared and pi squared canceling with factors of n and pi in the denominator here, and this 2 cancels this 16 down to an 8, which is what we see nicely summarized here. Okay, so we have 8 times 6 h bar squared, all these remainders together. And then we have a factor of pi squared left over times m times a squared. Now, what's highlighted here is the fact that we're summing up after reduction a 1 over n squared over the odd numbers. So we have 1 squared, 3 squared, 5 squared, and so on. What we can do is look at a table to find out what this series is equal to. Specifically, look up the sums of reciprocal powers, and what we get here is that this series specifically goes to pi squared over 8. How convenient is that? Holy moly. This cancels with the coefficient probability bracket with 8 and pi over 2, or pi squared, with the sum of that. That's remarkable. So here we have left over a total of 6 h bar squared over ma squared. So this tells us that we're looking like we're the superposition of several states, naturally, because of the style of wave function we have. It's not just an explicit state. Notice that the energy itself, the expectation of the energy, is not a given state because of the n squared. We would have 1, 4, 9. So the n squared here, there's no way to get 6 there. So, it's pretty cool to see how these combine together like this. Overall, these statements regarding how Cn connects to En are the quantum mechanic version of conservation of energy. And I guarantee you they're about to be used very heavily, especially with things like the harmonic oscillator and some of these other delta potentials and the free particle. So stay tuned, it'll be a lot of fun. As always, until next time, happy learning.